The one of the serious problems with falsification is the following. It's called confirmation holism. It's basically that you can never just test the theory itself. Sure, via modus tollens, if you have a theory T and it entails, you know, and you can derive test predictions P, then okay, T implies P. If you don't get the predicted results, then okay, that's not P, therefore not T. Hey, that falsified the theory, right? Well, that looks nice, but that doesn't work because, like I said, you can never just test the theory in isolation. There's always all these other background assumptions. So, when you test a theory, you have to assume a lot of stuff. Like, when we measure the results, you have to assume. You don't have to assume. You can check, but you still have to rely upon the accuracy of your equipment. You have to you have to assume that the laws of physics didn't suddenly change while you perform the experiment and then change back after the experiment. I mean, the point is, if you just Google confirmation holism, you can read about it. Actually, I'll put that in video description too. Yes, it's like you can have a theory and derive test predictions from it, and then if you don't get, then if you measure, and you compare what we physically measure to what was predicted by the theory, and if those things don't match up, you basically just know that something went wrong. Is it the theory that screwed up? Was it one of your background assumptions? So, logically, the form that this takes, it's not P implies Q, not Q, therefore not P. It's the conjunction of P1 and P2 and P3 all the way through, P sub n. All those together entail Q, then not Q entails, that P1 through Pn, at least one of those must be false. But see, only one of those conjuncts is the theory that you were trying to test, and everything else is just whatever you had to assume in order to to perform the experiments and just what I said before. The set of functions that that accurately model some physical behavior. Yes, that's a subset of all mathematical functions. Sure, that's true. But here's a problem within the philosophy of science. You see, we can only ever do finitely many tests. There are only finitely many experiments. So you can think about plotting this data on a graph, right? So the point is, you can, no matter how many experiments we do, we'll only get finitely many data points. You can mathematically prove that given any finite set of points, that there's an infinite number of lines that you can draw through those points. And a lot of people try to brush this off and just say, oh, we'll just go with the simplest one. Then you have to say what it is for a theory to be simpler. I mean, sure, the function f of x equals x is simpler than f of x equals sine of x. So if all the data points fall on both those lines, hey, let's just go with, f of x equals x. But I mean, there's much more to it than that. You could have a theory that posits more entities, but the math is simpler, so okay, so overall, is that theory simpler? There's very serious problems that you certainly won't be exposed to if you just do science, but in philosophy of science, we talk about it a lot. I really think that you're missing the point as to what the problem of induction is. You don't have to depend upon physical infinities to talk about the problem of induction. Suppose there's finitely many physical possibilities. So, I mean, so suppose there's only two. I mean, you could still have a problem of induction there. You can still say, okay, we've done all these tests. Right now, say there's theory A or physics A and physics B. Well, physics A is true right now, and it has been true for a long time. But again, if you try to say, therefore, it is likely that physics A will be true in the future, then you're using induction. And if you want to use induction, then the burden of proof falls upon you in order to justify it. So, I mean, a lot of what Everett was saying was negative arguments, where you just say, hey, look, here's something you're doing, you need to justify it, and he can just sort of pick away and knock down other people's attempted justification without having to put forth a solution of his own, or say that, he's not answering the question himself, but, I mean, that doesn't, it's not like that makes you justified if you're the one using induction. Again, if you're using induction, the burden of proof falls upon you. So if you can justify induction, I'd like to hear it, and I'm sure Everett would as well. By the way, Everett, I don't know why you backed off so much. What you've been saying has been fine, and then you try to defend yourself by, well, I lost at Warcraft 3. I'm really sorry that I was so pissed off. Things are fine. If you want to learn more about what the problem of induction is, again, I'll link you to my other video that talked about it.